The following video is about parametric equations, day 1. So the guiding question is, if we have an ant walking aimlessly around the ground or the coordinate plane, can we describe this using a function? And the answer to that question is clearly no, because the ant's path does not pass the vertical line test. So since we have something that doesn't pass the vertical line test, we can't describe this with a function. And also notice, this is not passing the horizontal line test either. So in order to describe this ant's path, we would have to use relations, and that can sometimes be somewhat difficult, especially if we want to describe where the ant is at any particular time. So something that is going to be a new concept for us is the concept of a parametric equation. So a parametric equation is, instead of using one equation to relate two variables, now what we're going to do is we're going to use two equations with two variables that we will then relate to each other with respect to a third variable. So oftentimes that third variable is time. We usually use the third variable as t, and it often represents some sort of time, but not always. So let's take example 1, a laser cutter is being used to carve out letters. We have parametric equations that are described by these graphs, x of t and y of t. The movement of this will carve out a single uppercase letter. T is in seconds, x and y are in centimeters. So the question is, what letter will be carved out? So if we look at what's happening, looks like it takes 7 seconds for this whole thing to occur. And it looks like the path is moving right, then left, then right. And while the path is moving to the right, it's not moving up or down. But when the path is moving to the left, so when x is decreasing, y is also decreasing. So it looks like in this 7-second interval, in the first 2 seconds, we move right, then we move down and left, and then we move right. So if we think about a letter that moves right, down and left, and then right, we would probably predict the letter Z. So if we actually plot where x and y, so this is x of t and y of t, if we plot where x and y are with respect to time, we see the 0.06, then the 0.26, then the 0.46. So what's happening is this graph moves to the right for 2 seconds, then down and to the left for 3 seconds, and then to the right for the last 2 seconds. If we want to be clearer on what's happening, we can give some arrows to help us understand where our parameter is moving the letter. And so that's what's happening. This would be a time 0, 1, 2, 3, 4, 5, 6, and 7. But again, if I didn't know that this was parametric, all I would see is this red path, even without the arrow markings. So I wouldn't know when anything was done. But knowing what happens parametrically, I can see that it's actually moving in this direction. And that's what's happening when you use a laser cutter or something. The laser has to move in a particular way in order for this to happen. Now we're going to predict this letter. So what we see is that the movement using parametrics for the first 2 seconds, the letter is moving to the right and down. And then for the next 2 seconds, the letter is moving only down. Then we have this dotted line, which is not moving anywhere. Or I'm sorry, it's moving, but it's not actually carving or engraving, so the machine just moves. And then finally, what's happening is the letter moves again left and down. So what I need to think of is a letter that's moving right and down, then straight down, because when this part is horizontal, that means that my X is not changing. So it looks something like this. And then my graph, or my laser thing, moves up without carving. So it's moving to the right and significantly up. So we were here, it moves to the right and significantly up. And then this blue section, it is moving to the left and down. So a good prediction would be the letter Y. And if I plot all of my XY coordinates, this is what's happening. So I move right and down, straight down. Then for 1 second, it moves up here without carving. And then it goes down again. So we're at 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds. There's no carving between 4 and 5. And then 6 and 7. Notice that at the second and the 7th second, the carver is at the exact same spot. Sorry, looks something like this. And then it moves in some sort of path this way, and then it carves down like this. Now we will consider the uppercase A that's shown. Using the directed paths, we figure out some of these points that are plotted. So I didn't have enough room to plot all of them on here, so I just picked a couple more. So I picked those points as well. And then we plot our x of t and y of t down here. So what we see is that this graph is moving to the right. Then it stops moving, or it stops carving, but it still moves. And then it goes to the right again. So this graph in terms of x of t, my horizontal movement, is always moving right. Whereas my vertical movement, the graph moves up, then down, then it does that 1 second of not carving, and then it's not moving up or down. So we see what's happening with the arrows kind of moving us in that direction. So that's what would happen with X and Y. And that shows us what's happening with this letter A. Now, can we write parametric equations for these things? And really, since all of these things are lines, that just means we have to be good at writing equations of lines. So the very first segment, which I will use the yellow highlighter for, is for the first 3 seconds. So notice that these equations are moving right and up. So the slopes are positive. Both have intersections at 0, 0, so it's easy to write them. Then my next set, I just write the equations of the lines. This equation stays the same because it's on the same line. And then from 3 to 6, notice that this graph is moving down. So since y is moving down, I need a negative slope. And notice that I used the point 3 for t and 6 for y, 3, 6, to indicate what's happening. So I used a point slope type of situation. Then, while I'm not carving, I need the graph to move along these dotted line linear segments. So it has to go from here all the way up to here. And so in terms of a line, notice that this line would be moving with slope 1. But since both of them are with respect to time, or -1, but with respect to time, I need it to move faster because it needs to get from here all the way up to here in 1 second. So that means that my x slope is -3 and my y slope is +3. Then finally, my y line is a straight line. That doesn't, it's a straight horizontal, vertical. It's a little confusing. But since this line on the A doesn't change y's, I need my y value to stay the same. And then x equals t minus 6, which if you looked at this equation here, notice that the y value is staying constant. The x value has a slope of 1, but it's a t minus 6 because if I extended it all the way down, I would end up with a x intercept. Notice that even though it's kind of like a y-intercept, it's actually an x value here. The intercept would be -6. Or if I plotted this point, I would say x equals 1, t minus 7 plus 1, if I wrote it in slope-intercept form, or I'm sorry, point-slope form. And then if I simplified, I'd end up with t minus 6. So that's how you can write parametric equations, and we're going to get a lot more practice doing that later.